Welcome to How'd You Think of That with Temple Grandin. I'm Sherry Quinn.
And I'm Rosalie Winard.
We are Grandin's co-hosts. We seek out big thinkers,
problem solvers, and curious minds
who approach challenges with unique abilities of their own, similar to the way our host, Temple Grandin, uses visual thinking.
When I was young, I thought everybody thought in pictures. And it was kind of a shock to me to learn that other people think completely in words. And it makes different ways of approaching problems.
We are joining Temple today on Zoom.
Hello.
Her home computer is in her kitchen, and she has two big posters taped to the side of her fridge.
Is that a new cow picture under the Hubble Space?
Yeah, I decided the Hubble Space Telescope needed a friend. So I've got cattle and I've got outer space together, two things I'm interested in.
If you're unfamiliar with Temple, she has Asperger's syndrome. This is a neurodevelopmental disorder now absorbed into the autism spectrum. A person with Asperger's is usually characterized by high intelligence, difficulty with social interactions, and a remarkable attention to detail and focus. In our first episode of How'd You Think of That, Grandin talks to Kyle Dawson, professor of physics and astronomy at the University of Utah. He studies the structure, origin, and evolution of the universe through observation using telescopes, spectroscopy, and other tools.
People always ask what you do, and I see your emotional breakdown in the responses I get. I see people who just give me a blank look, like, why in God's name are you doing that?
Why bother?
Or people are just immediately intrigued and want to know so much more.
Dawson is part of an international team of hundreds of scientists who are creating the largest 3D map of the universe. The mapping tool is called the Dark Energy Spectroscopic Instrument, referred to as DESI. It's a new type of camera placed on the 4-meter Mayall telescope outside of Tucson, Arizona. The camera contains thousands of tiny robots that operate fiber optic eyes aimed at the sky. The fiber optics capture the light from the galaxies and feed that light to a camera that reveals each galaxy's distance from Earth to allow scientists to calculate how much the universe expanded as the light traveled. DESI can survey 5,000 objects in the sky every 20 minutes. The main goal is to learn about dark energy, which makes up most of today's universe. Along with dark matter, dark energy is a complete mystery, preventing scientists from fully understanding the nature of the universe. Grandin and Dawson discuss his mathematical approach to research and how it differs from her visual one. They also address some of the snags in science education, where promising students can get left behind.
Seek knowledge, and people sometimes say, well, we ought to spend the money here on Earth. And I'm somebody who gets really turned on by seeking knowledge. Okay, you send the Voyager spacecraft out there, and Ed Stone is still monitoring it because it's still knowledge you can get from it. That's something I relate to. Okay, you're somebody that's seeking knowledge. Maybe you could just explain why you do it.
Yeah, I actually do it for exactly the same reason as you stated. I'm interested in knowing things to try to understand as much as possible about the underlying physics that drive our universe. That I find very compelling.
Yep.
So our experiments that we've been running for the last 10 years is trying to get at exactly that. We're using the cosmos as a large laboratory to measure fundamental properties of physics. And that is why I do it. And I just love to see what are the underlying laws of nature at the most basic level, the most first principles level.
I really like this whole idea of seeking knowledge.
Yeah, and we can seek knowledge in terms of what was the property or the nature of the universe, like only like a billionth of a billionth of a billionth of a second after the Big Bang.
Yeah.
And use that to model all the way out almost 14 billion years to today. So we're doing pretty well, but there's still some things we don't understand in terms of what's happening. There's still measurements we don't understand from a physical perspective, which is kind of fun too, because there might be new physics out there that we haven't yet discovered.
Well, I remember reading about how the deep space field picture got taken in the Hubble Space Telescope, and NASA thought it was kind of stupid to point the telescope at a piece of space that had nothing in it. And he hit the jackpot and found all those galaxies. That's why I've got my Hubble Space Telescope picture there on the side of the refrigerator, because when I try to think about things that you think about, I look at the deep space field.
I still use that image in some of my talks many, many years later. It's phenomenal.
But I only recently found out that the original proposal was to look at an area of the universe where there wasn't anything obvious to point it at. And then he was able to see way beyond, and he almost did not get funded for it. You see, this is the other thing on things that are really, really innovative. I tell my students, if your paper gets rejected from a journal, there's three reasons. Maybe it really is a piece of rubbish, should be rejected. Or it's something so new that nobody wants to believe it. Or pure politics. It goes against somebody else's theory.
Sure.
But lots of times people just don't want to believe something that's completely new. You're probably a mathematical thinker, and I'm a visual thinker, thinks in pictures. So things like designing steel and concrete work, for example, that's easy for me to understand. And I can kind of understand that there's a mathematics there. Because when I go online and I type in protein symmetry into Google for images, I get these beautiful geometric patterns, and they're inside our body. I'm going like, wow, maybe there's similar mathematics out there that explains our universe.
Yeah, so we have a mathematical formalism to describe the universe, and there are actually not that many numbers that go into it. So most of it's fundamental in terms of the way the physics laid out, and you have to plug in a few numbers to get the description of the universe that we live in. And one of the things that we're trying to do is find out empirically through experiment, what are those numbers? But yeah, we try to break it down to a very mathematical level. And that's actually why I like this type of field of science, is because unlike a lot of more complex organisms, it's possible to break it down to its fundamental mathematical form.
Or maybe something, like disease, like COVID, for example, turning out to be very complicated and has different reactions on different people. And they're not that well understood.
Yeah, and there's so many parameters there that you can only probably ever come up with general descriptions of the way COVID is reacting to people. You can never really make a specific prediction for a specific individual because there's so many things that we are probably never going to be able to understand. That's true of a lot. That's true of cancer. Yeah. That's true of other things. In our case, we think we can make very particular predictions for particular events out in the future. So that's a very distinct difference.
Well, because, for example, I'm in animal behavior, and but in all the sciences, they're doing all this mathematics on things, and they're trying to do some mathematics on things I don't think it's appropriate. And one is cattle behavior around waterers and feeders, and calling social behavior a random variable. I don't think so. They don't behave in a random way. Maybe there's a way to explain it mathematically, but not that simply.
Yeah, it's probably the case again where you can maybe describe certain patterns of behavior, but you're not going to be able to understand things at the level of predicting a particular cow's actions or a particular individual's actions.
Well, there's so many variables that go into it.
There's so many variables, and any mathematical model is only going to capture a subset of those variables.
So if you were going to explain how you'd explain your things with empirical experiments to somebody who's a non-mathematician like me, how would you explain it?
The way I view first principles physics is you can have a theory that presents a mathematical framework, and maybe you don't understand all the numbers that go in, but at least it produces a fully consistent mathematical framework. So it's almost like an equation without the numbers, right?
Okay.
And then the experiment, this is the way we look at particle physics as well. This is the way we're starting to look at a lot of cosmology. The experiment then goes out and tries to find out what are the values of those parameters that maybe we couldn't predict. And maybe as we learn more, our theory develops and sees that, okay, we didn't understand the equation well enough in the first place. As we've learned more, these numbers actually are connected in a way we didn't see beforehand, and we can develop the theory more and more. And the goal, which may never be achievable, is to have one equation where everything is fully predicted and you don't actually have to measure anything. That's probably impossible, but that's what we would call like the grand theory of everything. So that
and I think Einstein even was trying to do some of that.
Oh, it's been a goal
Yeah, it's been going on
forever.
Well, you have modeling I got to think of things I can relate to better, like, okay, weather modeling. And sometimes, is this hurricane going to hit here? They're getting better and better, but sometimes the hurricane veers off the side or it slams you worse than they thought it would. The modeling is still imperfect. In my own field, one of the things that I ask people to do modeling is how much of it is verified by real data. Because I think sometimes these models just get off into nowhere and they don't have enough real data to show if they're going to work.
True. So weather is a really nice example of kind of the boundary, I would say, between fundamental physics and more biological systems.
Yeah.
Weather really is particle-to-particle interactions that each can be described by our physics. But the problem is you get so many particles that you can't mathematically model all of them. So you have to go into this other regime of making, approximations over larger scales, and then you get to probabilistic predictions.
As a visual thinker, I kind of look at probabilities. Right now, I'm working on a book on visual thinking and why we need visual thinkers. And you take a mess like the Fukushima nuclear power plant accident, they never put in watertight doors. Simple, low-tech, watertight doors. That's a mistake I wouldn't have made. I don't know how to design a nuclear reactor. All I know is if that emergency pump gets wet, I'm in an awful lot of trouble. That's all I have to know about it. And I find sometimes in talking to certain people in mathematics that they wouldn't see the water filling up the site when the seawall is breached. Because that's a very, very, very basic mistake.
Yeah. I guess another way I see it in our field is there are people that really dive down into the mathematical details of a particular part of the problem.
Yeah.
But actually, in our case, in our field, a lot of times people are unable to step back and look at the whole big picture. And you still have to maintain that mathematical intuition.
Well, you certainly do, because you need that to design the reactor. I can't do that. But I would say, let's put watertight doors in there.
And we need that in our field to design the entirety of an experiment. And designing something that's going to take 10 years to build and 5 years to run. There's a lot of, filling in the gaps, the mathematical gaps with intuition when you do that.
Well, you see, you need both kinds of minds because they approach problems in different ways. And one of my big concerns in our educational system today, especially in the STEM fields, is we're screening out the people like me who can't do algebra. But you need us. Somebody has to, you have mechanical devices in some of your equipment. That's the kind of stuff I understand. So you need to have both kinds of minds working on things and recognizing that they have different ways of looking at things. You need to have both.
Many, many different types of perspectives. But yes, agreed.
What got you into physics in the first place?
It wasn't really that intentional of a process. When I was younger, I just always liked math, but I didn't really understand in my schools, in middle school and high school, I never really had a very good understanding what physics really was. I've tried to remedy that in my kids' school. So I go and give talks to my kids about what makes physics the fundamental branch of science. But yeah, it wasn't until I got to college that it almost was a little bit of process of elimination that I found physics just more appealing than I did math or chemistry. But it really was not, there wasn't like an aha moment per se. It was more of experimenting with lots of different things.
I talked to another person who's a physics person, and they told me they hated chemistry. And when I look at it, chemistry's a lot of math in it too. And you seem to be one who likes physics better than chemistry. What is it about chemistry that some of you physicists don't like?
God, I don't want us to go on to the record. But I'll say this. I liked physics more than I liked chemistry. And part of the reason was that the equations really could be broken down into something that was really, really physically motivated from first principles. It wasn't any approximation. It wasn't using a technique that I hadn't been introduced to. And you could really build up your model from first principles all the way down to more complicated systems. And I think that I found more appealing.
You obviously seem to like physics better. And chemistry, I mean, you've got more different variables that can affect it, like the how you mix the stuff together, temperature. I review a lot of journal articles of people don't put in just basic stuff like what breed of cattle you used in your experiment, or what type of labware you used, which can totally change your results.
Sure. And from my perspective, that all is really important to understand, of course. But when you're first starting out in the sciences, you're kind of given those formalisms or those equations that describe the way things mix in chemistry without understanding why those formulas came out in the first place. Whereas physics, it really goes from the ground level. And I think that's what I found appealing.
You can look at the formula and it really explains it.
Yes. And then you build up the complexity from there.
You're finding a lot of good students coming into your field now?
So yes, there always have been a lot of good students. I always wonder in the long term, as we learn more and more and more, and the field becomes more and more advanced, this seems to be true of all fields. You know, at what point is there a gap between what a student can learn as an undergraduate and what a student needs to know to enter into research? Because at some point, the research becomes advanced beyond what's accessible from undergraduate. I always worry a little bit and wonder where we are with respect to that scenario.
Well, I talked to an agronomist about 2 years ago about monoculture and agriculture, and we need to be doing more biodiverse crops and things like this. And one of the things he told me, he says, I got these graduate students, postdoc, straight A's, very narrow, no creativity. Gets so narrow, as Isaac Asimov talked about in one of his science fiction stories. You become an expert in one subdivisional sliver of nothing.
Yeah, so there's two aspects of it. One is the individual becomes so narrow, it's hard to do other types of work. And the other is that narrow point that the person's achieved is so long that it becomes unachievable for somebody to reach out of undergraduate. How do you bridge that? So there's really two consequences.
You are listening to How'd You Think of That with Temple Grandin. We are joined by physicist Kyle Dawson. He studies the fundamental principles of the universe and is also involved in many STEM education programs. The United States is falling short on its STEM workforce, a major driver of economic stability and success. It's projected by the National Association of Manufacturing that the nation needs to fill 3.5 million STEM jobs by 2025, but is on track to fill less than half of that amount. The deficit comes at a time when the demand for STEM jobs is rising. According to the Pew Research Center, employment in STEM occupations has grown 79% in the past few decades. The bottom line is STEM needs to be where the kids are, when they are most curious.
You look at something like going to the moon. Why was this important? Well, every school kid was turned on by that and wanted to study science.
In fact, Grandin's career was inspired by her high school teacher, Mr. Carlock, who cultivated her interest in science and taught her how to build things like model rockets, and he challenged her to figure out how some optical illusions were created. This part of her life was featured in the Errol Morris documentary called Stairway to Heaven.
And one of the science teachers used that as a way to motivate me in schoolwork and says, well, you ought to try to figure out how to make one of those. But he wouldn't just give me a book and show me how to do it. And then he gave me one hint. He let me look at a picture in a book for like 15 seconds. And then from that, I was able to figure out how to make the trapezoid window and the Ames distorted room illusion work.
Grandin follows in the footsteps of her mentor. STEM education is something both she and Dawson foster, not only in higher education, but also in kindergarten through high school, where early exposure to the sciences can nurture young minds by igniting ideas. As Dawson pointed out, he exposes kids to math and physics in a way that gets them excited about these often intimidating subjects.
I've taken two angles to that. The first is to just kind of show the big, exciting videos that we would all relate to. What we would find exciting is also exciting for a first grader. one of the favorites is a video of the sun reaching the end of its life, expanding up and swallowing the earth. So I think all of us would be very fascinated by such a video, and first graders are equally fascinated. So that's one approach. And then there's the more technical approach of just pointing out the things in life that we all deal with every day, whether it's like a light or a light switch or some electricity or a ball rolling down a hill, and just try to make the general point, which is something that a first grader can actually understand, or a second grader can understand, that you can see a simple event and use mathematics to fully describe it. And that's the whole concept of physics. And oddly enough, that's not something I understood as a senior in high school. So I've tried to remedy that intuition that was lacking in my upbringing through no fault of my parents, but I've tried to bring that to kids at a very young age. And I think it's possible. It's all about the tie-in of math to what we can see in our everyday lives, and even things that are more subtle than we see in our everyday lives, but still affect us. So that's the general idea I try to make. And that works at a very young age.
I get fascinated. I get science and nature, and I'm seeing these beautiful geometric patterns in proteins, in material science stuff. And some of it looks like cathedral rosette windows. I'm going, that's chemistry? Wow. I don't understand the math behind it, but that just blows my mind. And those are some of the things I suggest to parents to show to kids, to get them turned on about, mathematical things. There's a lot of kids that are gifted in math. Nobody's doing anything to develop it. Or my kind of mind, we're growing up, the kids are growing up today, they never use tools. They don't get a chance to do stuff that might develop some of these skills.
Yeah, that's all correct. And I have a lot more insight into what's going on in elementary school now than maybe I did 5 or 10 years ago. Mm-hmm. And I'm really seeing a lot of the challenges and opportunities that are there. So hopefully our school systems can allow a little bit more of that exploration beyond just meeting the standard core. And I think that would, that's kind of what we need a little bit more of that flexibility and allowing kids to explore in the classroom.
I remember one time I took statistics with some of the early statistics programs, and you have to make a model for statistics. Well, I just made up data sets. I just made them up. And then I'd throw variance into it, throw a few outliers, and watch what it did to the significance level when I just messed with the data. And I found that was a lot of fun. And then a week later, they changed all the software, and I didn't know how to do it anymore.
Oh.
And my statistics teacher goes, well, where'd you get all these models? And I said, well, I made them up because I wanted to see what the program would do. You see, I'm kind of a bottom-up approach. What will it do if I throw 2 outliers into this data, 30 data points?
I actually play similar games when I teach graduates in their first semester, graduate students. I think it's very good to build up that intuition, actually.
Maybe Sherry should give the wrap-up question. Okay, Sherry.
I was really curious to hear about your latest discovery, I guess, or latest mapping of the universe that's giving a clear picture of the cosmos. If you could summarize that, and also why is it important that we understand and get this clearer picture of the cosmos?
So our experiment was based in New Mexico, and it ran for about 10 years. It was a very large fraction of my life and a huge commitment of my life. We were out to measure the 3-dimensional distribution of matter in the universe over as much of volume and as much of period of cosmic history as possible. And that in itself is great for visuals. It's compelling to see a 3-dimensional map of the universe. But our goal is to take that map and to compress it into basic statistics, like how do you quantify certain features in each of those epochs of cosmic history. So we try to simplify it into basic statistics And then those statistics that tell us about how quickly the universe was expanding or how quickly matter was growing at each time give us a means to test those models I was talking about earlier. We have a model that describes all the universe from a billionth of a billionth of a billionth of a second after the Big Bang up until today. We can then use that model to fill in what components of the universe exist, how much of them exist. And our goal is just to understand by looking at how the universe has evolved over these billions of years. We have about 11 billion years that we explore. Looking at how the universe has evolved, what are those underlying physics that describe it all? And we've done extremely well. There's no magical number of what precision is needed, but we're basically at the level for some of the most fundamental things of describing the physics at the 1% level, at 1% precision. And it's really robust. We really understand as we change the model this way or we change the model that way, how our model responds and how it describes the data. We're actually doing a very good job at this point. And in the next project, we're hoping to get another 10 times better in our sampling of the cosmos. And that should get us even further down the road in understanding how the universe has evolved.
I can really relate to why do we seek this kind of knowledge. And then I'll give you one little thing from animal behavior. There's a scientist named Jack Panksepp. He died about 2 years ago, really great neuroscientist. And he kind of identified the core emotions in people and animals. You've got fear. That makes you avoid predators. Makes you drive carefully, when there's ice on the road. Fear, avoid danger. Then you have anger. You want to keep that under control. Then you separate the calf from the mom. The two get upset, separation anxiety, and humans that be grief. Then you have this other urge called seek. And you have certain cattle, if you put GPS collars on them, they'll go out and just graze all kinds of strange new pasture. And there's others that won't do that. It's a high seeker, urge to explore. And then, of course, you got sex drive, you got the mother-young nurturing, and then you've got play. Somebody that's higher in the nurturing, they're going to say, well, let's spend the money here on Earth. But I can really relate to the seek to do new things. And if you want to see something really funny, look up a video, remote controlled car and cattle. And when the remote controlled car first goes to the pasture, they all run from it. And then they start chasing it. They went from fear to seek. I just want to thank you so much for coming here, because I think it's just so important that different kinds of minds to start to learn how to understand each other better.
This has been really enjoyable for me.
Oh, good.
That was scientist Temple Grandin and physicist Kyle Dawson. Join us for our next episode with scientist Eric Jorgensen, professor of biology at the University of Utah.
Sitting in the shower, I suddenly realized, oh my God, I can change the genome. With a DNA break, I can put in whatever I want.
He studies how the brain works and is a rare visual thinker like Temple.
The meeting of their minds is an explosion of insights into the nature of discovery and how to nurture more creative minds.
I'm Sherry Quinn.
And I'm Rosalie Winard.
Thanks for listening to How'd You Think of That with Temple Grandin. How'd You Think of That is produced in partnership with the Utah STEM Action Center.